Right. So next topic is Laurent half-shade polarimeter. Laurent's half-shade polarimeter. So this is a device used to study the polarized light from any given sample. Most often with liquid samples. I mean, especially used for chemical analysis. Okay, certain materials polarize the light into a particular direction, especially liquid samples. So how far they tilt the polarized light? I mean, they try to rotate the orientation of polarization by some angle, depending on the nature of the material. I mean, each liquid sample will have a different angle of polarization. They flip or they tilt the polarized light by a certain angle. So how far the tilt can be measured using this half-shade polarimeter. Okay. So for that, the basic construction is we need to generate polarized light first of all. So I am taking a light source and generating parallel beams. Monochromatic light source. So I am taking a monochromatic light source and generating parallel beam of light rays. And from there, I will be generating plane polarized light using a polarizer. Collimator used to generate parallel beam of light rays. Then polarizer. So it is a polarizer. It generates polarized light. Plane polarized light. So now at this stage, I am going to introduce tube with liquid sample. Okay. So మనకు కావాల్సినటువంటి లిక్విడ్ శాంపిల్ ని ఇక్కడ ఇంట్రొడ్యూస్ చేస్తాము. అండ్ ఇక్కడ వస్తున్నటువంటి లైట్ రేస్, సో హియర్ ఐ యామ్ గోయింగ్ టు యూస్ క్రాస్ నికాల్. Okay, I'm using a cross nickel. So if there is no liquid sample in between, the output light intensity is 0. So I am taking a polarizer and an analyzer in a cross position. So if there is no liquid sample in between, my output light intensity is 0. So when I introduce this liquid sample in between, it turns the direction of or orientation of polarization by some angle, some 20 degrees or 30 degrees, whatever. So then I try to rotate this cross nickel till I get 0 intensity again. So I record the reading for initial orientation. with zero intensity without sample and introduce a sample, then I will observe some light here, then I start rotating this cross nickel till I get zero intensity again. Then the angle rotated by this cross nickel will be the angle of rotation produced by the liquid sample. Right? So that is a basic setup for polarimeter, which measures the angle of polarization produced by liquid samples. But the problem here is we cannot exactly identify the zero intensity. So initially we may consider a particular location as a zero intensity, but that may not be exact zero. Right? And after introduction of sample also, we are rotating this nickel to identify the zero intensity location, but our human eyes may not identify it perfectly. So to overcome that problem, we are going to introduce a half shade plate in between. I am going to introduce a half shade plate in between. So this consists of a normal glass and a quartz glass. It consists of two half pieces cut into two half circles and joined together. One is normal glass, another is quartz glass. This quartz glass is a half wave plate. So that flips the light by 180 degrees. So when light incidents on it, let's say at an angle like this, so this is the original incident direction. Okay, so what happens? This half wave plate flips this light ray, polarized light ray by 180 degrees. So this is the incident, and this is 180 flip. So incident polarized light direction is in this way. Let's say if the incident light ray is along this direction, in the second half of the region, this quartz plate acts as a half wave plate, so it flips the light ray by 180 degrees. So what happens? All we see is only a portion of the plate will have maximum intensity. Okay, so only half of the portion. If the orientation of the incident ray is tilted, we will have one part on a normal ray, another half will be flipped. But if the incident ray is along the axis, if the incident ray incidents like that, what happens? If you flip it, it will be in the same direction. So I am saying the second half is flipped like that. It means what? This portion will not be there. Whereas if the light ray or polarized light ray incidents exactly perpendicular to the plate, what happens? Even after flipping, it will fall on the same line. Right? So both portions will be visible with equal brightness. So if the incident light ray is a bit tilted, what happens? Only upper half of the plate is more intense and lower half of the plate intensity reduces. Whereas if the incident ray exactly falls normal to the plate, like along the junction of the plate, then flipped ray also follows the same path. So we will see equal brightness. So this is just to fix the orientation of incident light. So we are ensuring the incident light ray is exactly coming along the vertical direction. So then cross nickel can be exactly set at 90 degrees with respect to this half shade plate. I mean, we don't need to bother about the polarizer. Now the reference point becomes this half shade plate. So once you set the incident direction, I mean, if you are able to see the entire plate is illuminated uniformly, the polarizer incident direction is vertical to the plate. Otherwise, what happens? Only a portion of the plate will have higher brightness, other portion will have lower brightness. So this ensures the incident direction is exactly vertical. Then you can set the cross nickel 90 degrees with respect to half shade plate. So then your calculations or your measurements will be perfect. Okay. So ultimately, we are taking a monochromatic light source. We are generating parallel beams using collimator, and we are generating polarized light out of it using a polarizer, that is also a nickel prism. And we are using a half shade plate to ensure the orientation of polarization set to vertical. Then we are introducing a cross nickel 90 degrees with respect to the half shade plate, so that outcome of this analyzer is zero intensity. The light coming out of this cross nickel will have zero intensity. And now we are going to introduce a tube that contains our liquid sample in between polarizer and analyzer. So this rotates the orientation of polarization by certain angle. So now we will see some light through the analyzer, and again we try to rotate the analyzer by certain angle till we get zero intensity, right? So that gives you the angle of rotation produced by the liquid sample. This is used to study the optical behavior of liquid samples, especially in organic chemistry. Majority of the chemicals exhibit this. I mean, there is a separate branch of chemistry called stereochemistry, which deals with polarization, polarizing nature of the samples. So the angle of rotation produced by the liquid sample, theta is proportional to the length of the tube. More the length of the tube, more will be the angle of rotation produced, and it is also proportional to the concentration of the liquid. More the concentration, more the material, more will be the angle of rotation. So it is given by theta is equal to SLC. S is called specific rotation. So it is the angle of rotation produced by 1 unit concentration liquid in 1 unit length tube. Specific rotation S is equal to the angle produced by considering 1 unit length tube and 1 unit concentration of the liquid. Okay, so usually we consider the length of the tube in decimeters. Length is measured in decimeters and concentration grams per centimeter. Okay, let's say this is 1 decimeter. 1 decimeter అంటే ఏంటంటే 10 centimeters అని రాసుకోవాలి, లేదా 2 decimeters ట్యూబ్ తీసుకున్నారు. అప్పుడు మన ఫార్ములా ఎట్లా రావాలి? అవర్ ఎయిమ్ ఈజ్ టు క్యాలిక్యులేట్ దిస్. S is equal to theta by LC. So ultimate formula is S is equal to 10 theta by LC, where L is measured in decimeters. And this is measured in grams per centimeter. So this 10 is introduced to balance that factor of decimeters. The last topic in this series is LCD display, liquid crystal display. Liquid crystal display, which you use in your calculators. Okay. So it consists of liquid crystals ఏంటంటే అవి they are the group of crystals in a liquid state, but their orientation can be controlled using electric field. So they behave like crystals, like a solid material, but they are in liquid state. That's why they are called liquid crystals. The behavior is perfectly oriented, just like crystals, and they are in liquid state. So and their orientation of polarization can be controlled by using electric field. ఎలక్ట్రిక్ ఫీల్డ్ యూజ్ చేసి దాని ఓరియంటేషన్ మనం కంట్రోల్ చేయొచ్చు. సో ఇక్కడ ఏముంటుంది, ఇది కన్సిస్ట్ ఆఫ్ సబ్స్ట్రేట్, so it is built in a set of layers. The bottommost layer is called substrate. Okay, Next to the substrate we have light source. And next to the substrate you have light source. And a polarizing filter. They are not shown in the diagram in the textbook. So substrate, light source, polarizing filter. So next to the light source you have polarizing filter. So this ensures a particular orientation of incident light. So next to that you have liquid crystal array. So all your liquid crystals are packed here next to the polarizing filter. Substrate, light source, polarizing filter followed by liquid crystals. Then electrode. So this carries whatever content you would like to display. The shape of the electrode is same as the text you would like to display. Then analyzer. Otherwise this is also a polarizing filter. Followed by glass cover. So what is the overall structure? So we have substrate, light source followed by polarizing filter. So we get polarized light. Next to that the liquid crystals and then electrodes. So when you apply electric field to these electrodes, they try to tilt the liquid crystals in their location. So usually the crystals are oriented so that the polar light directly passes through the crystals without any objection. So what happens when you apply electric field at the location of electrodes, the crystals will get tilted. So that polarized light cannot travel through them. So in those locations we will see dark band on the glass plate. So when you apply electric field, wherever the electric field is applied, the crystal orientation change and output intensity becomes 0. So we see dark bands wherever that electric field is applied. Right? So that is a backlit type LCD liquid crystal displays. If the backlight is not used, the top cover is most transparent so that light enters the entire array and the substrate consists of a reflector. So instead of this light source you will have a reflector. You are not using backlit type LCD. Instead of light source you will have a reflector so that the light enters from the top cover and reaches the bottom surface electric field, at those locations light transmission blocks. Okay, so there are two types of LCD displays. One backlit type LCD display, another normal display where light enters from the cover and reflects back from the surface, from the substrate. Okay, that's all.